All right, today we're going to crack open a really key concept from linear algebra. But look, forget the dusty textbooks. We're going to do this as a spy story. Because, sometimes the most elegant and powerful secrets, they're not in some classified file. They're actually hidden right inside the math.
So, I want you to imagine something. Let's say you're an intelligence chief. You've just put together this elite team for a supercritical mission. But how do you know for sure they're a perfect team? I mean, how do you test each spy's abilities and, maybe more importantly, guarantee they won't get in each other's way?
Well, it turns out that mathematics has a single, almost surprisingly elegant answer to this. There's a test so powerful it can verify your entire team with just one single calculation.
Okay, so our mission, should we choose to accept it, is to figure out if we have a perfect team. And in the world of math, that means we're looking for something very, very specific.
And that specific thing is called an orthonormal basis. I know, it sounds kind of complex, but just think of it as our perfect team. For any team to be perfect, every single member, or, in math terms, every vector, has to meet two really strict rules. First, they've got to be unique. That means they work in their own lane, they don't mess with anyone else's job. In math, we call that orthogonal. And second, they have to have a standard strength, a value of exactly 1. We call that normal.
All right, so to run this test, we're going to need two groups, the team we're actually investigating and, of course, the investigators. Let's meet the key players in this little math drama.
First up, the suspects. We'll represent them as the columns in a matrix we're just going to call A. So here's suspect number 1. Let's call him C1. He's the vector 1, 0. And here's our second suspect, C2, the vector 0, 1. These are our two spies. And our mission is to prove that these two are the perfect team we've been looking for.
Okay, now for the detectives. They're created from something called the transpose of matrix A, which we just write as A with a little t. All this means, really, is that we take our column vectors and we just flip them on their side to make row vectors. So our first detective becomes the row 1, 0, and our second becomes 0, 1. And here's the cool part. These detectives are now perfectly designed to interrogate our suspects.
And this is really the crucial part. It's a one-to-one relationship. Detective number 1, that first row of our A transpose matrix, is built specifically to check on suspect number 1. Detective 2 is built for suspect 2, and so on. It's a perfectly matched system.
And now, it's time for the main event. It's time for our detectives to finally question the suspects. In math language, this is where we do a matrix multiplication. But for us, this is the interrogation.
Yeah, and there's a really great way to think about this that comes straight from the source material. The calculation, A transpose times A, is basically a self-interrogation. The matrix is literally using its own parts, the detectives that came from its rows, and the suspects that are its columns, to check itself out, to verify its own integrity. So how does this interrogation actually unfold? Well, it's a very systematic process. First, Detective 1 questions Suspect 1. Then Detective 1 moves on to question Suspect 2. After that, it's Detective 2's turn. He questions Suspect 1. And then finally, Detective 2 questions Suspect 2. See? Every detective questions every single suspect.
And what we get from all this is a brand new matrix, which you can think of as our official interrogation record. Each number in this record is the result of one of those questioning events. Mathematically, that questioning is an operation we call the inner product. And it's actually really simple. You just multiply the matching numbers from the detective's row and the suspect's column, and then you just add up the results. Let's see exactly what that looks like.
All right, the interrogation is done. The results are in. Let's take a look at the record and see what the verdict is. Did our team pass the test? So, what happens when a detective questions their own target? Let's check. We'll take Detective 1, that's 1, 0, and have him interrogate Suspect 1, also 1, 0. We multiply the first numbers. 1 times 1 is 1. We multiply the second numbers. 0 times 0 is 0. Then we add them up. 1 plus 0 equals 1. A perfect match. This 1 is the proof that our suspect is normal. They have that standard strength we were looking for. Okay, but what about when a detective questions the wrong suspect? Let's try it. We'll have Detective 1, 1, 0, go question Suspect 2, 0, 1. First numbers, 1 times 0 is 0. Second numbers, 0 times 1 is also 0. Add them up, 0 plus 0 is a big fat 0. And that tells us they are orthogonal. There's no connection, no interference. Perfect. So when we put all 4 of our interrogation results together, we get this matrix. The ones running down the diagonal, that proves every single spy is normal. The zeros everywhere else, that proves every spy is orthogonal to all the others. This final result is the famous identity matrix. And for us, it's the definitive, all-clear signal. The team is perfect. Okay, let's just pause for a second and appreciate how powerful this is. I mean, why does this one single matrix give us the complete answer to everything we needed to know? Well, this shows it perfectly. It's because we're running 2 tests at the exact same time. Those ones running down the main diagonal, they confirm that every single one of our vectors is normal, that they have that required standard strength. And at the same time, the zeros everywhere else, what we call the off-diagonal elements, confirm that every vector is orthogonal to every other vector. They are all unique. So, you see, the whole thing boils down to this. We started with 2 totally separate conditions we needed to check. The normal test, a vector's inner product with itself has to equal 1, and the ortho test, a vector's inner product with any other vector has to equal 0. The amazing thing is that the single equation A transpose times A equals I wraps both of those checks up into one beautiful, super compact statement. And that brings us right to the grand conclusion, really the fundamental theorem of this whole explainer. The columns of a matrix A are orthonormal if and only if A transpose times A equals the identity matrix. That's it. That's the definitive test. So the real takeaway, the thing to remember, is just the sheer efficiency of it all. Instead of running a whole bunch of different individual checks, you do one single multiplication, and the shape of the answer tells you everything you need to know. It is truly the most compact and elegant test possible. And that really makes you wonder, doesn't it? If a whole spy interrogation is hiding inside a simple matrix multiplication, what other elegant stories, what other powerful ideas are just waiting for us to find them inside the rules of mathematics? That's it for this explainer. Thanks for joining me.